So good morning, everyone. My name is Alejandro Bohe. I'm new to this community. I'm part of the SWOT project, and more specifically part of the team that derives the algorithms, in particular for the ocean processing. So today I'll try to explain a little bit how we measure significant wave height, in particular, from SWOT data at resolutions of a couple kilometers. I should really point out that a lot of people in the SWOT, so ADT stands for Algorithm Definition Team, and also in the Calval teams have contributed to this thing in one form or another. And then some people have provided external data that I could use to do some validation. So Fabrice provided WaveWatch 3 spectra. Luc and Bia provided mass data, so LiDAR data to compare against, and Andrea Hay and Benoît Legrésy provided buoy data. So here's the sort of the outline of this talk. The first part will really address the summer school part of this meeting. I'll try to be as pedagogical as I can to try to explain how we go about measuring SWH. A lot of people ask me this question: what's the principle of the measurement? So I'll try to describe that with a few, at least a cartoonish explanation. And so that's really how we produce maps like this one in detail. And then, of course, I have to convince you that these are not just, like Fabrice was saying, not just pretty pictures. They look very nice, but do they contain real and accurate data? So there's a second part here of the talk where I will show you some comparison against external data. And I'll finish with a few examples to illustrate what we think is in this data for you to do science with it. All right, and then there's the stuff I won't be discussing for the sake of time. I'm happy to discuss those things with you at a coffee break, if you have any questions, of course. One of them is the characterization of the measurement error, which is a bit tricky because we're really looking at small scales. And so we have this mixture of instrument error, of course, that we always have when you do a measurement. And then there's also all the small scale signal that it's really hard to separate between the two, right? But I have a few things to show later if you're interested in these things. There's also one thing that I need to mention, which is, so all the results I'm going to show today are not what you would find in the current versions of the SWOT product. And the reason for this is this SWH measurement stuff is very much something that we're developing as we speak. And so, and of course, changing operational code isn't a very fast process. So if you go and fetch a SWOT product right now, you won't get the same quality of data as the one I'm showing here. And I won't spend too much time talking about the artifacts that you would find in the SWOT data. We had a few questions on Tuesday evening at the pizza and remote sensing. And so if you do look into the current version of the data and you see stuff that you don't really make sense of, please come talk to me or send me an email afterwards, and I can try to explain what these things are. But expect biases in that version of the data. The instrumental effects that we need to account for, that I'll describe in a second, haven't all been properly accounted for. And so there's biases and all sorts of artifacts in there. The one thing I would say, though, is that those biases are pretty large scale, so long wavelengths. And so if you're interested in the small scales, you might get a bias or something, but the small scale, the dynamics in the small scales, or the spatial variability in the small scales should be pretty fine. And then the last thing I'm not going to talk about, and then I'll move on to the actual talk, but the last thing is I'm not going to talk about resolved waves with SWOT. So the SWH measurement that we're making here is not one where we really resolve the waves and then look at standard deviation. It's really sort of an integrated measurement within the pixel. I'll explain that in a second. With SWOT, we can resolve some of the waves in particular. So the data, the SWOT data over ocean, it has gone through an onboard processing where there's some sort of massive averaging on board to reduce the amount of data that we need to downlink. And so the resolution of that is, depending on how you define resolution, is about 500 meters. So waves that are larger, wavelengths than that, we can resolve. And that's what Fabrice's poster is about. And I'm sorry, Fabrice, I thought you were going to show a couple of images here. But please come see Fabrice's poster to see how we can use those very long and follow these very long swells. And then there is a limited coverage of higher resolution data that we acquire with SWOT. This is designed for hydrology, for measuring stuff over rivers and lakes. Over ocean, there's a limited amount of coverage of that, and so there you can start playing the game of looking at things at a finer resolution. There's complications in there, also so non-linearities in the instrumental measurement. But if you're interested in that thing, of course, again, just come and talk to me. The current version of the HR products are not very suitable for that kind of analysis, but we can work on making this a bit more practical for ocean analysis. All right, so that's the end for the part that I'm not going to discuss. And so let's start with trying to explain a little bit how we do the measurement. All right, so for this, we need to explain, so I've tried to be as schematic as possible, not to burden you with heavy notation or anything like this, but we need to understand a little bit what SWOT is, what's the primary, the raw SWOT measurement, so that we can understand how we derive the wave heights from that. And of course, I'm sure you all know that SWOT is primarily a topography mission. It's there to measure the surface height. And the way you do that, well, you have these two antennas. So one of them is emitting, but then the signal is backscattered by the surface, comes back to the two individual antennas. And so for each, you have to really to understand that for each image, for each pixel in your image, you're really measuring one complex field at each antenna with an amplitude and a phase, and also some noise. And so the way you go about measuring surface height is by looking at the phase difference, essentially, which you can so the phase difference is linked to the difference in these two paths, and you can do the geometry and derive surface height from that. And I'll insist one more time that this is not the way in which we're measuring waves, because really we don't have the resolution to resolve the waves and look at the standard deviation. So that's what SWOT is primarily doing. Of course, we're measuring these four different real numbers, so two independent complex numbers, so that's four real combinations that we can use. And so we can actually use the other three combinations to do something. And the obvious choices are, of course, just use SWOT. Don't do any interferometry using the combination of the two antennas. Just look at the individual powers, and you get two SAR images, right? So that essentially means take the modulus squared of each complex amplitude. That will give you SAR images. Basically, I'm saying that you can process these things into sigma naught, right? And then you can try to infer whatever you're trying to infer, say, on Sentinel-1 images. This is sort of the same imaging idea. And then I've talked about three different combinations, phase difference and individual amplitudes or intensities. And then there's this fourth combination here, which we're going to focus on and from which we're going to derive the waves. And this is what we usually call interferometric correlation. Maybe you've heard the term coherence. And so what that really is the norm here of the interferogram, so the cross correlation between the two complex numbers, the two signals at each antenna, normalized by the individual intensities. So really think of this as a normalized covariance of these two complex numbers, S1 and S2, and so that's really a number which is going to be between 0 and 1, because it's normalized covariance. And the question now is, how do we get the waves from this? How is this related to the waves? How does this sense waves? So some of you might have seen this kind of plot. This is the effect of waves. So as a function, the colors here are significant wave height. As you increase significant wave height, you decrease this volumetric decorrelation. I'll talk in a minute about why we call this volumetric decorrelation, but this is really sort of this quantity when you have waves. And so this depends on cross-track distance, really on incidence angle. As you move away from nadir, you can see that your correlation approaches 1, so you have less decorrelation. Intuitively, the fact that this decorrelation increases when you increase significant wave height kind of makes sense, but we're going to explain this in a second. The more waves, the more decorrelation you're going to get in your system. And so what we're going to do in the next 10 minutes is try to explain really why things increase with significant wave height and why you get more decorrelation in the near range for low incidence angles rather than in the far range. All right, so we need to look a little bit into what the measurement is. Again, so you have your two SWOT antennas. Yeah, thanks. Do you want me to try? All right, so I've attempted here for this presentation a sort of a cartoonish explanation of why this is sensitive to the waves, why it has the right dependence. So schematically, what you need to understand is that, so the numerator here, let's focus on the numerator. So that's the product of the signal at the first antenna times the signal at the second antenna conjugated. What this really is so what the radar is doing, for this, we're going to focus on this for any given pixel in our image, okay? What this really is you look at all the scatterers that go inside that SWOT pixel, and we're going to describe this in just a second, and you sum their contributions up with each with its own interferometric phase, okay? Whereas for the individual powers, you just sum all of the contributions from the different scatterers inside the pixel. And of course, there's all sorts of instrumental terms there, antenna gains and whatnot, and point target responses. I'm really trying to be as schematic as possible so that you understand the sort of the essence of the measurement. All right, so there's really just two things that we need to make sense of to understand this quantity here: what scatterers are inside a given pixel, and what is their interferometric phase. All right. So let's start with interferometric phase. Seems like I can't move the presentation now. Okay. So can I find your back? Does this work? Yeah. All right. So let's start with interferometric phase. And what this is really, as I said before, this is the difference between these two red paths here. So let's start with a very easy case where you're really at nadir, which we're not even looking at with SWOT. Then the two paths are exactly equal, and there's no dephasing between the two, meaning the interferometric phase is just 0. Okay, but then if I'm looking at a different point further here, right? So more in the getting away from nadir, more in the far range, then these two red distances, these two red paths, they start becoming different, and so you get a non-zero interferometric phase. So we've just, in very simple terms, established that interferometric phase, increases as you move away from nadir. That's really the dependence of this one thing. All right, and then we need to make sense of what's inside a given pixel, and that's pretty simple. So again, I'm cutting a few corners. I'm doing this just in this plane perpendicular to the track of the satellite, but just to sketch the explanation. Well, what's inside a given pixel? Well, a radar just works by integrating over all the points which are the same distance. A given pixel is a given distance from the radar, okay? So you just need to look at all the points at the same distance from the radar. And so if you look at a particular incidence angle here that I've chosen, well, all the points at the same distance from the radar are on a circle. That circle is a very large radius circle because this is in space, so this is about 900 kilometers. So instead of showing you a circle here, I've just plotted a line which is the tangent to the circle. I'm guessing you'll understand what I mean here. And so what are all the scatterers that are inside this given SWOT pixel? Well, there's only one of them in this case. It's this point here. I've taken a flat surface to start simple. And so we're saying everything on this line here and on the surface will contribute to my SWOT pixel. There's only one point in this flat surface case. So I'm just integrating over a point. This dephasing is whatever it is, but when I take the norm here, which was the numerator of my decorrelation, the phase just disappears because there's really one contribution inside this integral, and so it's cancelled out by the denominator. There's no decorrelation. I just have 1 point. There's no decorrelation in the system. That makes sense. Now, what happens when I start putting a wavy surface in here? Well, so this is the same line as before. This is this iso-range circle. All the points in here are the same distance from the radar, and so they all fall inside the same pixel. But now, because this is a wavy surface, I start getting several points, okay? And those points, well, they have different interferometric phases because we've established that interferometric phase increases towards the right, okay? So this point, and all of these points, they all are inside the same pixel. They all contribute to this integral, but all with different interferometric phases. And so when I do this sort of coherent sum here, because contributions are not in phase, this integral starts in absolute value being much smaller than this one, and so I'm getting decorrelation. So that's really the principle behind the system. So I do get decorrelation, and so this is really saying waves do create decorrelation if you define this as this gamma decorrelation measure that I've defined before. Okay, we're almost there. So what happens now if I go to a larger incidence? So this is the example I shown before, and so now I'm moving on to the next one where I will just increase this incidence angle here, but keep the surface the same. And so now if I increase this angle here, what I'm doing is, so this circle here, this iso range, is just perpendicular to the incidence angle. So if I go to larger incidences, I'm just making this straight line here steeper, and so it will just intersect for the same surface less points, which means that the interval of interferometric phases that I'm having contributing to my numerator integral is smaller, so I have less decorrelation. Okay. And last thing, which is pretty obvious, if I increase the amplitude of the waves, then again I start having a larger. I start having a larger interval of interferometric phases contributing to my summation, so I'm getting just more decorrelation. All right, so that was the sort of the cartoonish explanation, which sort of hopefully explains why the decorrelation from waves has this shape. So as you move to larger incidence angles, much less decorrelation, and of course as you increase the amplitude, much more decorrelation. So that's great. Let's just measure the decorrelation from the SWOT data. Use these to invert as a function of cross-track distance. So for every pixel, you get a correspondence between SWH and decorrelation. Do the inversion, and we're done, right? And that's the end of the presentation. Unfortunately, there's many other things that create decorrelation in the data. I'm not going to try to explain all of them. One of them, which is a bit intuitive, is, of course, you have measurement noise in each of your pixels. This is not correlated between the two antennas, so it will contribute to the decorrelation. In fact, it's the vastly dominant contribution to decorrelation. There are other geometric effects linked to the fact that the resolution of the radar is not infinitely good, so you have integration of all sorts of geometrical intervals. And I'm going to skip all of this. The only thing, so the summary for this slide here is we measure the total decorrelation from the data. We're interested in the part that I just sort of sketched before, the contribution from the wave, and there are all these other things to undo. So you have to model them very accurately to try to invert, divide the measured decorrelation by the known terms, if you will, and then get to the contribution from the waves. All right, so should we be worried about those known terms? Is it easy to get them sufficiently accurately that you would, invert the waves then without any problem? And the answer is no. And so I also got this question a couple of times this week, because for some of you, maybe you were in the SWOT discussions maybe before launch, and everyone in the SWOT project was extremely cautious about saying we will measure waves with SWOT. And that was the reason, really, that these known terms, known with a lot of quotation marks, are hard to model. They contain a lot of instrumental effects, artifacts that you need to account for very accurately to actually have an inversion which even makes sense, right? Out of the box, when we turned the SWOT on, the waves that we would get were, meters off. Okay, but that was just the fact that we really needed to understand the instrumental effects that were polluting our inversion. So this is just one slide to summarize this. What I've done is plotted, so this plot I've already shown you, and this plot is as a function of significant wave height, the bias that you would get, or the error that you would get in significant wave height if you were making an error on your measure of decorrelation, which is of the order of 10 to the minus 3. Now, of course, 10 to the minus 3 without any context doesn't make much sense, right? It's a small number, but really, how difficult is it to attain 10 to the minus 3? I'll get to that in a second. But even this tiny number, which I've chosen for a reason, would give you, well, depending on, so the colors are different cross-track distances. And as we already established, in the far range, so large cross-track distances, the decorrelation is very small. And all these curves are just, a bunch together, which means it's going to be very hard. You're almost insensitive to the effect of waves in this regime. So a tiny error on decorrelation will give you a huge error on significant wave height, right? And so at 60 kilometers, so in the very far range, the limits of the SWOT image, you would get errors of several tens of centimeters, or even for low significant wave heights, almost a meter or so. Okay, so if you control your volumetric the instrumental effects in your volumetric decorrelation to 10 to the minus 3, which is a challenge, as I'll explain in a second, you're still making errors of tens of centimeters on significant wave height. And you'll notice that not only does the error increase with cross-track distance, again, that's the fact that here the curves are all together, but also the error increases as you decrease significant wave height. And that's the fact that here, essentially, the blue and the orange are closer together than the last two ones, right? So you're also less sensitive for small significant wave height. And so really what you have to remember from all of this is that the most challenging regimes are the far range, okay, and small significant wave height. That's where, and when you look at the data, then please keep this in mind, that these are going to be the most challenging regimes. This is where most likely you're going to see biases and artifacts. All right, so I hope, in my case, this is hard, this is sort of easy. All right, one last thing about the method, and then we can look at pretty pictures. So 10 to the minus 3, that was the value that I chose in my previous plot. Is that a complicated target to shoot for? And it turns out it is, right? And so from the launch until now, until a few weeks ago, what we've been working on is really try to characterize the different instrumental errors or contributions to the decorrelation, and those are actually much larger than 10 to the minus 3, which really means you have to model them pretty accurately. Now, if those instrumental errors were static, those would be very hard, very easy to calibrate. You just, whatever empirical calibration you want to apply, you measure your errors, and then you apply this correction, you're done, right? The hard part is really when, and that's actually what happens, those errors start having a time dependence. And particularly, they would, most of what we've seen is that these errors evolve along the orbit for a variety of reasons, because the signals that we emit along the orbit change. We need to change the pulse repetition frequency of the instrument, which changes the PTR. And so, really, I'm not going to bother you with any of those the technical details about this, but really the hard part of the work was to characterize all of these contributions, these instrumental contributions, and model them so that you wouldn't need to empirically calibrate them. The last thing we wanted to do is to empirically, because when you do empirical calibration, most of the times you don't have the right parameters to describe the root causes of your perturbations, and so you end messing things up, right? So the hard part was really, let's try to model all of these instrumental contributions, and I'm pretty happy with the work that we've done there, because we've gotten to a point where we are mostly only left with static contributions, which I'll tell you in a second how we deal with them, but we don't see, or almost don't see, any variation. The variations that we keep seeing, which are time dependent, are sort of the order of 10 to the minus 4, which is, one other magnitude below what I've shown before, and so very reassuring. But if you, so as I said, the dynamic part, I think we mostly dealt with this. There's still a static part that we need to account for, and so one way to see this is if you compare the measurements that you get from, because I'm hoping most of you know that SWOT has two instruments. There's a nadir altimeter, and then there's Carin, which is this interferometric instrument that gives you 2D images. And so one thing you can do is compare the SWH measurements from nadir and from Carin, and hope that at least, of course, they're not measuring at the same location, right? But if you've gotten rid of all the instrumental effects accurately, then you can hope that on average, significant wave height should be the same, right, at nadir and then everywhere in the image. And so if you try to do this comparison, you find that you have sort of a systematic static bias in the volumetric decorrelation. And I'm plotting this bias here. So effectively, this is the calibration that we apply. And I want to be very clear about what this calibration word means in this context. So you can do this comparison for a few hours of SWOT data between nadir and Carin. And what you see is that at the level of volumetric decorrelation, not at the level of significant wave height, you have a constant bias, which looks like this, which is a bit different for the two SWOTs because it's polarization dependent. And so what this means is that you really should add, before doing your inversion, you have the effect of the waves, and you have all these known terms, hopefully known terms. And then this summarizes what we don't know about the instrument, but that we've worked hard to remove any contribution which is not constant. And so, to be very clear, this was derived by using a few hours of data and comparing SWOT's nadir with Carin. But this comparison we do once, we derive this sort of static calibration, and then we apply it. But whenever we do then a SWH estimation with Karen, we're never using the SWH from nadir again, right? We could turn the nadir off, and we would still get the same estimates from Karen. So we're not dynamically calibrating Karen to the nadir, is what I mean. If that makes sense. All right, so enough with the method, and now I'll show you pretty pictures and then try to convince you that those pretty pictures are science. So the inversion, just to finish on, so those are two examples. I'm showing two, so this is the same example really, but when I do the inversion, what I do is I can average, to beat down the noise really, average the volumetric decorrelation to resolutions, which I choose, and then do the inversion. And so typically I do these inversions at 2 and 5 kilometers. And the idea of course, this should get a bit noisier, although, again, separating noise from small-scale contributions is not easy. But also, of course, the hope of going to this small resolution is you can look at finer scale phenomena, in particular things like group modulations will look different, at least partly different, in the 2 kilometer and 5 kilometer data. All right. So how do we, okay, I explained how we get the measurements, but now we will need to explain how we validate them. So for this, the best thing we can do is try to compare with external data and see whether the comparison goes somewhere. So these two plots are, again, so often I'm going to show 2 kilometer resolution and 5 kilometer resolution just for comparison. And these plots are as a function of cross-track distance. So this is, this has a sign from -60 to +60 kilometers. So I'm really looking at the two SWOTs here. And I'm comparing with the nadir altimeter, which is again an independent measurement, up to the fact that we've used a few hours to do the static calibration. I've accumulated statistics over, I don't know, a couple of hundred passes from the one-day phase. Again, as I said before, the assumption when we do this validation, because the nadir and Karen are not measuring at the same location, and we know that SWH has spatial variability, but on average, you can probably expect that if you average enough, the SWH from Karen and from nadir should be the same. And this is what we get. So we essentially get bias. So the colors here are different bins of SWH. And you can see that the biases that we get in the end are sort of centimeter scale, but you can also see that they increase slightly for lower SWH values, which is what I said before. Lower SWH is harder, right? We're less sensitive for low SWH. And I'll just briefly mention this sort of funny shape here, which is related to the question Gwendal you had, I think, on Tuesday afternoon. So what you're seeing here is a residual of not perfectly accounting for some instrumental effect, which has to do with perfectly characterizing the actual point target response in flight. So while I think the quality of the data that we're getting now with this new version is much better, you still will see, in particular at small SWH values, you will see some artifacts. These comparisons, so that was the comparison with SWOT's nadir. This is a different comparison which has been shown before a couple of times in this meeting, which is the comparison with the LiDAR data from the mass sensor. So very different measurement in that it really individually resolves the waves, and then inside a given box looks at the standard deviation. So there's I don't know, more than a dozen flights that we've looked into. Most of them compare very favorably. So this is one example where, of course, this is the 2D image is Karen's data, and then there's a collection of dots here, which are the mass measurements. It's of course hard to see at this scale that the agreement is particularly good. So I've plotted here the 1D profile where black would be mass, and then red and green would be Karen at the two different resolutions. And so the plot below is the difference between Karen and mass, which, as you can see, and you have a histogram of the differences here. Differences of the order of a few, centimeters to a bit more than a couple 10 centimeters. What I really like and what really, gives me confidence that we're really seeing things at small scales is stuff like this very sharp gradient here around 35. So this is this sort of bluish region here, where over a few tens of kilometers you have an increase in SWH of a few tens of centimeters, and this is really seen in the same way by mass and carrying, so that's really encouraging for the small scale. What the last plot here, which I haven't explained, is the time difference between mass and carrying, because of course SWOT, goes through this area in about less than a couple of seconds, so it's a nearly instantaneous measurement. While for mass, which is over this aircraft here, it can take tens of minutes to hours to look at the same area, and so in doing all these comparisons, you have to account, or at least keep in mind, that there's this time difference between the measurements. And in terms of sea states, as you all know much better than I do, hours can make a lot of difference. So typically, what we see, and I think Gwendal showed a similar plot, as you increase the amount of time between the two observations, you typically increase the differences that you see. But if you restrict to differences in time of about an hour or so, you see very, very good agreement. And this was just a zoom for you to look at the agreement in 2 dimensions. Another independent measurement is comparisons to buoys. So this is data provided by Andrea Hay and Benoît Legrézy. So they have this moored buoy in the Southern Ocean, which was conveniently placed under the 1-day repeat phase of SWOT. So I'm not sure I said what the 1-day phase was. So SWOT was first put on a 6 months, for 6 months on an orbit where it was revisiting the same areas every day. Then it was moved to what we call the science orbit, which has global coverage, but of course you don't get to see the same points as often. But because this was under the 1-day phase, for every day we essentially have a co-located measurement between SWOT and the buoy. And so this is the time series. So this is again a nice comparison. So first of all, because it's completely independent data, and also because it goes through, because this is Southern Ocean, it goes through very different regimes in SWH, and you can see that the agreement is, well, the scale here is not terrible to see the agreement, but the agreement is pretty nice across all SWH regimes. I should have said, so red and blue are carrying. I've also put the nadir in green, although the nadir, is not at the same location as the buoy. The buoy is actually in the center of the swath, so there's also more difference in the nadir because of this, not just random noise. And those are the differences plotted as a function of the sort of scatter plot of differences between carrying and the buoy as a function of SWH, and you can see that the errors are typically pretty small. Those are the histograms here. And so again, that's why I left the measurement characterization of the measurement error for discussion afterwards, because it's hard to extract from these differences to attribute the width of the differences to just measurement noise. There's measurement noise in any other instrument, in the buoy, in the LiDAR, and there's small scale stuff which is not exactly resolved in the same way, so it's hard to really infer measurement noise from this, but at least let's say this is an upper bound on the measurement noise. Last validation. So how am I doing with time? 5 minutes. So I won't really go in details over this validation. This is external validation against nadir altimetry. This is the Sentinel-3 SAR satellite that Fabrice. So the kind of nadir measurement that Fabrice was mentioning at the end. So here we've looked at one crossover between SWOT and Sentinel-3, where essentially the agreement is very good in the regions where Sentinel-3 is behaving well, as most of the time. And then there's, in these very large swell regions, we know that the noise in the Sentinel-3 in SAR altimeters kind of goes a bit crazy, so I'll switch to this. This is sort of a 1D profile of the comparison. And you can see that there's a region where the noise in the nadir instrument and also in Sentinel-3, they start going a bit crazy. But the carrying profile is really well behaved, and so overall the agreement is very, very good. And it also turns out that carrying is behaving pretty well in these high swell regions. So let me just finish with a few examples, and I'll be pretty quick because some of these were already discussed this week. The main point I want to make here is that SWOT is. And I think that was one of your conclusions. SWOT data is amazing, at least I'll try to convince you of that. And one of the reasons why I think it's amazing is that it provides at the same time these different measurements of the surface. So really at the same time and at the same location, you have SSHA, so surface height, from which you can derive the geostrophic parts of the currents. There's we're looking at small scales, so geostrophy might be, you have to be cautious. Also, if you have unbalanced motions here, you're going to mess up your currents a little bit, but you have some approximation to the currents. On top of that, you can use the backscatter images to infer things like predominantly wind, but there's certainly a lot of other physical contributions in there. Currents will have a signature, biological processes will have a signature in there. And then you have significant wave height, as I've just explained in the first part of the talk. And so basically, you can start trying to play the game of what correlates with what and find physical explanations. And that's really one of the things why I think SWOT data is particularly valuable. So I'll flash through a couple of cases. This is a case where so this is the SWH field. So this is somewhere in the Gulf Stream. One day where the winds were not very strong. So the SWH here is about 1 meter. And you can see that you have this huge correlation between the SWH field and the sigma naught field, which was very puzzling and also very worrying to me, because my main worry was, of course, this is an artifact, right? Those two shouldn't be that correlated. And so maybe I've done something wrong in the inversion that causes this. I've tried to be as careful as possible for that not to happen. And when I do systematic comparisons, I don't see any trend in sigma naught. One way I can try to convince you that this is maybe physics is the following. So this is, again, the sigma naught field and the significant wave height field. And I've done the following. So very simple, naive physics here. But let's take the significant wave height field measured by Karen and try to assume that this is only due to winds, like local winds blowing right now and creating these waves, which we can argue about. Assume that have a relationship between significant wave height and wind, just using a very simple Ardhuin spectrum, saying, the small scales and the large scales are determined by the same thing, just the wind. And then use a geometric optics, very simple model to predict the backscatter from that wind field derived from this. And I get this image, which of course looks very similar to this one, because that's the input. But what's striking is that quantitatively, if I then compare the sigma naught that's measured by Karen and the sigma naught that's reconstructed from my SWH field, not only do they look very similar, but also quantitatively, if I make the difference between the two, I'm getting rid of most of the structures in there, which is sort of saying that winds are a plausible root cause for the two observations. It's certainly not a proof that this is wind, but it's saying it might be that wind is causing these patterns in the sigma naught and the patterns that you've seen before in the SWH. Another example, which is, so that was sort of studying the correlations between SWH and wind, or one example where the correlations were very strong. Another example was described by Bia, where you can look at the correlations between waves and so this is SWH, waves and currents. Here from these pictures, you can see that there's a lot of correlation. And Bia showed a few of these cases and discussed some of them. So if you zoom in, you can see that, I don't know how well you can see them from the room, but there's this sort of SWH streaks going across the current, and which align pretty well with the direction of propagation of the wave. This is one of the WaveWatch 3 spectra that Fabrice provided. And so that really sort of points towards the fact that there's actually physical content in these images. Almost done. This is just another example. In fact, if you open the data at sort of random places, very often you kind of see these SWH streaks. So that's one thing that we can look into. One additional source of variability is wave groups. We've heard a lot about this, just from Fabrice before, from Gwendal and others in the previous days. So what I've just compared is, so the expectation, of course, is, this was pointed out before, you can have two spectra with the same total significant wave height, but which have very different shapes and very different pickedness. So this is just two examples here. Same significant wave height, and so this parameter that Fabrice introduced before, measuring the pickedness of the spectrum. The units are wrong here. This should read kilometers anyway. So you would expect that for a peakier spectrum, you get much more small-scale variability in the waves, and so even by eye, that's what you see in this map here as compared to this one. And so I think, again, SWOT provides a way to quantitatively look at these things, maybe infer things about pickedness from just just the local variance of SWH. And also for us, for C-state bias corrections, this might be important because if we're able to resolve local SWH, we could in principle apply better C-state bias corrections. One last thing I'll point out here is that you can see that and this is what Fabrice was describing before, not only do you see these modulations in Karin, but also, you know, in the nadir, you sort of see correlated modulations. So here it's yellow, yellow. So I may be reading too much about this, but in many cases that I've looked at, you know, in the very near range of Karin, you do see this strong correlation. Almost done, 2 more pictures. One of the, as I said before, low SWH is a hard regime for us because the sensitivity is less. And so one thing I very briefly looked at is what happens sort of in lagoons where you don't expect a lot of significant wave height. So this is one example in New Caledonia. Where, so I'm sorry, those 2 plots contain the same information, except this one has the nadir and this one has the coast, and for some reason I just couldn't put them on the same plot. There was a bug. Anyway, so just think of these as the same plot. And so in just around the coasts here, you know, you have the sort of the lagoon where Karin is actually seeing very low significant wave heights. So this is sort of saying that we can push this thing towards the coast, and we can expect that the data will be sensible, although I don't have any validation data there. So if you're interested in these kind of regions, there might be really something to learn from the SWOT data. But again, I'm not sure what the accuracy is in these regions. And you can also see there's this super high SWH region just around the coast, which is, of course, an artifact. And so that's the fact that within within the averages of 2 or 5 kilometers that I'm making, sometimes I get contaminated by land or by other features, and so this just create artifacts. So expect in this data set that they're gonna be some artifacts. So this is yet another example. I'll just point out here. You can see there's a sort of a stripe aligned with the flight direction of the satellite. Just be very cautious. Those are usually artifacts, of course. And this is what I was mentioning before, that the point target response is perfectly aligned. So in some regions, you can see weird things. Last example. So we've looked at the very low SWH regime in this lagoon, and it's sort of sensible. This was an example of a storm where the SWH peaks at about 12 meters, somewhere here in the, so this is the Domingo storm, last November. And I'll just, flash this pictures here. These are different sections of the plot I was showing before. And you can see, so again, not much validation data here, but just a comparison against the nadir sort of tells you that the data in this very high SWH regime looks pretty reasonable. Again, those things would need to be quantified. And that's the summary. Not going to read all of this. I'm just going to say Karin provides 2-dimensional maps of significant wave height at resolutions of kilometers. So that's kind of new at a global scale, and I'm sure there's a lot of science to be done with it. There was a lot of work to make sure that all the instrumental effects, we could get rid of them as much as we could. We're pretty happy with the state of things, but of course this is work in development. We've validated this against different independent measurements. Looks pretty good. And so for the first time, we have at this global scale maps of, at the same time, of SWH, currents inferred from heights, and sigma naught. And so I'm hoping there's a lot of science that can be done with this, and that's for all of you to do. Thank you.